We're going to conclude our discussion of gravity today by discussing where we observe it most often, which is on the grand scale of objects orbiting one another. And additionally, we're going to discuss Kepler's laws, which describe how planets move around the sun. So first, with some quick definitions, the orbit of anything is the path that a satellite follows as it moves around a celestial, or in other words, an astronomical body. So an astronomical body or a celestial body can be a star, it can be a planet, it can be a black hole, it can be anything like that. And when we talk about the path that a satellite follows, now normally in our head we think of satellites as man-made satellites, like communication satellites, GPS satellites, but really a satellite is any object that just orbits another object. So for instance, a couple of satellites we could say is the moon is a satellite of Earth because it orbits around Earth. The Earth and all the other planets are satellites of the sun, and additionally, like GPS satellites orbit Earth, so they are still satellites, but it's not just those man-made ones, it's all these what we call natural satellites too. Now we discussed these in class, but Kepler's laws of planetary motion, which were developed by Johann Kepler in the early 1600s, described how planets move around the sun, and he figured these out just by looking at reams and reams of experimental data, or observational data, in fact. The first one is that every planet orbits the sun in an ellipse, so an elliptical orbit, not a circle, with the sun as one of the two focuses, or foci, of the ellipse. So this is one focus, this is the other. First off, this is not the scale, of course, but this is also greatly exaggerated, and we'll talk about that later. Kepler's second law is that a line joining each planet to the sun sweeps out equal areas in equal amount of time. So this is a little more convoluted, but what we're saying here is that I have a line connecting the sun to this planet, and in some time, the planet has moved to this new position, and whatever that time is, we'll say it's a couple months, for instance, a little t, and it has swept out this area as this line has moved from here to there. So we have this area here. Well, if we look at a different point and the planet's orbit, well, in the same amount of time then, so whether that is 2 months or whatever, it must sweep out an equivalent area. But for that to happen, when the planet is closer to the sun, well, then it must move a greater distance around its orbit in that same amount of time in order to make this happen. And if that's the case, this is really ultimately telling us the planets orbit faster when they are closer to the sun. They literally speed up when they get closer and slow down when they get further away. And the last of Kepler's laws is even more convoluted, and specifically says that the period of each planet's orbit, squared, is proportional to the length of the semi-major axis cubed. So in other words, capital T squared is proportional to A cubed. That's the mathematical way of representing this. So if I look at this orbit here, so it's an ellipse, so we call this the minor axis, it's basically the short diameter, and this is the major axis, the long diameter. So the semi-major axis is specifically looking from the center of this elliptical orbit, not at the sun, at the center, to this point here, and it's essentially like the long radius of the ellipse. So that cubed is proportional to the period it takes for the amount of time it takes for a planet to go around the sun squared. That's a lot, but ultimately really what this is just telling you is that planets further from the sun take longer to orbit. That's ultimately what it comes down to. Now, while Johann Kepler was able to describe how the planets moved around the sun, he didn't provide any reason why they did that. And that really came from Isaac Newton with his theory of gravity that we discussed largely last class. But how do we connect gravity to an orbit? And that is where this thought experiment that Isaac Newton came up with called Newton's Cannonball is very, very useful. So let's imagine a scenario here where we have the Earth, and we have a really gargantuanly tall cannon that fires a cannonball out of it. Now, we learned in projectile motion that when a cannon is fired horizontally, the cannonball will take a parabolic trajectory and hit the ground. But in this situation, this is such a tall cannon that not only is it going to take this trajectory, but it's going to keep falling until eventually it hits the surface of the Earth. So, if we fire the cannonball, maybe it takes this trajectory here. But let's say we fire the cannon so that the cannonball goes faster now. Well, if it goes faster, it's going to cover more distance before hitting the ground, which means it's going to go around more of the Earth before it hits the ground. If we go even faster, it goes even further. Now it's going all the way to the other side of the planet. And eventually, if we go fast enough, we actually cause it to go all the way around and hit the cannon in the back. So what's happening here is that when the cannonball is fired, it is moving so fast that as it falls, as it's being pulled down by gravity, it's falling, but it's matching the curvature of the Earth. It is going so fast that even though gravity is pulling it down, it will continually go around the edge of the Earth, continually miss the edge of the Earth. And so this is an orbit. An orbit is just a result of an object moving fast enough that it continually misses the planet, even though it's being pulled down by gravity. So, this specifically is what we would call the orbital velocity, the speed it takes to do this, specifically for a circular orbit. So this is the minimum orbital velocity, so the minimum speed you need for the cannonball to go all the way around, because it makes a perfect circle here. But what happens if we fire the cannon even faster? Well, if we start to do that, it's going to start looping out further away from the planet, but it's going to be pulled eventually back. So now I fire it even faster, okay? And I fire it even faster again. And what we notice, as we fire it faster and faster and faster, the circular orbit begins to morph and shape into an elliptical orbit. So as the orbital speed increases, we go from a circular orbit to an elliptical one. And in fact, this is ultimately giving us an explanation for Kepler's first law, that planets orbit the sun in elliptical trajectories, which just tells us that they are going faster than the minimum orbital speed that they need to continually go around the sun. If they're going at that minimum, they would be making a circular orbit. If they were going slower than that, they wouldn't be able to orbit. They would get spiraled into the sun. But let's say you go even faster. Well, if we go fast enough, you're going to go so fast that you're actually not going to loop back around. And in fact, you're going to reach something known as escape velocity. So if the projectile goes not too high, too fast, the projectile goes too fast, it will literally escape the orbit of the planet and be able to move beyond it. So for instance, if we want to go to Mars from Earth, we have to go as fast as this escape velocity, like a rocket would have to, or else it's just going to be pulled eventually back down to the planet. You have to reach this speed to move beyond the gravitational pull of Earth. Now, a real quick note on a misconception that a lot of people have. So, it's not really that hard to think about that planets move in elliptical orbits instead of circles, but usually when you see diagrams of these, the elliptical orbits are really dramatic. So like if this was your sun, you've got this really crazy big elliptical orbit, so that really at one point the Earth is super far away from the sun, and at the other point it's much closer. And if that was the case, we would not be able to survive. That is way too big of a difference. And in fact, this diagram I'm showing you here is actually showing you plotted out the trajectory of, so this is the sun at this point. This is the trajectory of, for instance, Mercury, of Earth, and of Mars. And the dotted lines are what they would be if they were perfect circles. Now for Mercury, yeah, it's a little bit eccentric. It's not really a perfect circle. It's definitely a little elliptical. Mars is a little bit less, but the Earth, as we can see, this is the what we call the eccentricity, that Earth is really just about 2%. An ellipse. It's pretty close to being exactly a circle. So when we see these diagrams, just know that's greatly over-exaggerated. Really, most of the planets, and Earth in particular, actually have near-perfect circular orbits. They're just a little bit elliptical. And the reason why that's so useful is that if Earth moves in essentially a circular orbit, well then we can analyze its orbit using what we've learned about uniform circular motion. So, as the Earth goes around the sun at some distance r from, the distance between the centers of the two, well, we know for a fact that its velocity will just be 2 pi r over the period, that tangential velocity. And additionally, we know that the acceleration of the Earth toward the sun will be the centripetal acceleration, v squared over r. And additionally, that the centripetal force of the Earth and the Sun, so specifically of the Sun on the Earth, will be towards the Sun and will be mv squared over r, where m would be the mass of the Earth and v would be its tangential velocity. But remember, the centripetal force is the net force. It is not a specific force type. And what is that net force? Well, that is going to be the force of gravity. So the force of gravity is literally the centripetal force pulling the Earth towards the center, causing it to orbit around and continue this circular pattern. Additionally, that tells me that the centripetal acceleration is actually just g. That g, that gravitational field strength, is really equal to the centripetal acceleration, not specifically the gravitational field strength of the Sun at the position of the Earth. Well, knowing that the centripetal force, or mv squared over r, is literally the gravitational force, can allow us to make some interesting connections and learn some interesting insights. So specifically, I've got Fg is equal to mv squared over r, where Fg is the net force, the only force acting on the Earth as it orbits around the Sun, and Fc is the centripetal force, mv squared over r. And let's go ahead and substitute in for Fg what we learned was the gravitational force from Newton's universal law of gravitation. And if we look, that is g big M little m over r squared. Now, a couple things to remember. Big M would be the mass of the Sun. Little m would be the mass of the Earth. And if we look at this, we have gmm over r squared is equal to mv squared over r. Well, the mass of the Earth actually cancels out. And additionally, one of the r cancels out. So instead of having r squared, I'm just going to have r on this side. And I get that v squared is equal to gm, big M, over r. And if we take it a step further, then v is equal to the square root of big G, big M over r. And this equation, v is equal to the square root of gm over r, is actually the equation for the orbital velocity. It's the equation for the speed that Earth needs to maintain to continually go around the Sun. Now, granted, this is for a circular orbit, so this is really that minimum orbital velocity it needs to maintain that orbit. But the orbital velocity is in meters per second. G is the gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. M is the mass of the object being orbited. So in the Earth-Sun situation, it would be the Sun. If it was the Earth and the Moon, that would be the mass of the Earth, and we would be looking at the Moon's orbital velocity. And additionally, r is the distance that that satellite is orbiting at. Now, specifically, it's really the distance of the center of the object being orbited to the center of the satellite. If they're far enough apart, we can really assume those radii aren't going to matter too much, but for a lot of things, we do need to keep that in mind. So let's remember that. Now, a couple things to note here is first that the mass of the satellite actually doesn't matter. So if I took Earth out and I replaced it with just a tiny rock, and I had the rock move at the same orbital velocity as Earth, well, then it's still going to be able to maintain that orbit around the Sun, because the mass of the satellite is inconsequential here. Additionally, something else to notice is that as r goes down, as we get closer and closer and closer to the orbiting body, well, the speed has to go up to maintain an orbit. And that sounds a little familiar because this is really just another restatement of Kepler's second law, that when planets orbit closer to the Sun, they have to move faster. Now, granted, this is for an elliptical orbit, this is for a circular orbit, but the same idea is generally applying, that as you get closer, the speed must be bigger. So now let's look at one more interesting relation. We now have two equations for a satellite's velocity as it orbits some object. Now, one of those is the orbital velocity, and one of them is the tangential velocity, but both of those still apply. So specifically, now this is, remember, for a circular orbit. Well, let's go ahead and plug in the equations we have for those two. And that would be the square root of gm over r, okay, we just learned that one, and 2 pi r over t, which we've known now for a few lessons. Well, how can I get something useful out of this? Well, let's go ahead and get rid of the square root. So I'm going to actually square both sides of this. So when I square both sides, the square root's going to go away. And when I square the other side, remember you have to square every individual piece. So you're going to get 2 squared, pi squared, r squared, period squared. And in fact, we're going to get something that looks like this. So now we have gm over r is equal to 4 pi squared r squared over the period squared. Okay, well, let's take it a step further. Don't like dividing, so let's go ahead and cross multiply. And if I cross multiply, I'm going to get t squared over here. Instead of having r squared, I'm now going to have r cubed. And in fact, that's why I end up with gm period squared equals 4 pi squared r cubed. And now I'm going to take the additional step of dividing both sides by gm. And end up here. And lastly, okay, so this is 4 pi squared r cubed over gm. I'm just going to basically pull r cubed out. I've literally done nothing different here, just pulling it out of the parentheses to isolate it a little bit more. So I have the period squared is equal to 4 pi squared over gm times r cubed. So we now have this convoluted equation, period squared is equal to 4 pi squared over gm times r cubed, where specifically the period is the period of a satellite's orbit in seconds. Now, that's not very useful a lot of times because usually we have so many seconds in an orbit, it's often on the order of years or even decades, but that's okay, we can convert to something else once we find it, but it needs to always be in seconds. G is the gravitational constant, m is the mass of the object being orbited, not the object doing the orbiting, not the satellite, in kilograms, and r is the distance that the satellite is orbiting at, specifically the distance between the centers of the two objects in meters. Now, something important I want to note here, though, is that this may be an ugly equation, but it looks a little familiar. And the reason why it looks familiar is that we learned previously from Kepler's third law that the period of a satellite's orbit is proportional to the semi-major axis cubed, and this was specifically for planets in their elliptical orbits around the sun. Well, the thing is, though, is that this is basically telling us that for a circular orbit, if we have a circular orbit, we're not going to have a major axis and a minor axis. We're going to have the same distance all the way around, so the same radius. So A is going to become r. And so if we look at this, the period squared should be proportional to r cubed, and in fact that is the case, because if we look, this is a constant, that's a constant, that's a constant. For the planets orbiting around the sun, this is a constant because it's the mass of the sun, so that's all a constant. So I have r cubed times a constant gives me period squared. They are in fact directly proportional in that way. So this tells me, once again, that planets further away from the sun are going to take longer to orbit, and we've basically proven this specific relationship with Kepler's third law by using elements we got from Newton's theories. Okay, let's do one practice problem before we call it a day. So, given the following information, which includes the mass of the sun, the mass of the earth, and the distance between the centers of the earth and the sun, let's determine A, the orbital velocity of Earth around the sun, and B, the period of the Earth's orbit around the sun. So go ahead and do this on your own, pause the video, try your best, come back, and let's just see how you did. Well, hopefully you gave it a shot, so let's look at the first part, the orbital velocity. Well, that's equal to gm over r, where I'm going to substitute the gravitational constant, and then m is the mass of the sun. It is the mass of what is being orbited, not the mass of the satellite, divided by r, that distance between them, and I take the square root of the whole thing, and we get an orbital velocity of 29,750 meters per second. Incredibly fast. To put that in perspective, the Earth is moving through space at about 18 miles per second. Very, very quickly. So to find the period, I'm going to use the period squared equals 4 pi squared over gm times r cubed. I'm going to go ahead and stick with the numbers I have. So the period squared is equal to 4 pi squared, r is 1.50 times 10 to the 11th meters. We're going to cube that over g times m. Once again, m is the mass of the sun, not the mass of the Earth. In fact, we didn't even need this for any of our calculations. That was just extra information. And we get 1.00 times 10 to the 15th seconds squared, but you know, this is t squared, so let's take the square root of that. And when we take the square root, we get about 3.17 times 10 to the 7th seconds, which is great, but not very useful to think about. So let's go ahead and actually convert that into a number that's going to be more familiar. Let's actually specifically convert it into days. So if I'm going to convert to days, so I've got 3.17 times 10 to the 7th seconds. Well, there are 60 seconds in a minute. Remember to put 60 seconds on the bottom so my seconds cancel. There are 60 minutes in an hour, and there are 24 hours in a day. So I'm going to multiply or divide this number by 60, then by 60 again, and by 24, and we get 366.7 days. which is approximately the length of Earth's year, which makes sense. Now you'll notice the number is not exact, and part of the reason that is because this was for a circular orbit, and Earth's orbit, while very circular, is not quite circular. It is in fact elliptical, so we should have a little bit of a discrepancy. That's okay. So what are the main takeaways for this lesson on Kepler's laws and orbits? Well, one, can we describe the underlying ideas of Kepler's laws of planetary motion? That planets orbit around the sun in ellipses, that they move faster when they're closer to the sun, and if they're farther away, it takes them more time to go around. Can we conceptually explain how a satellite will orbit an object despite being continually pulled by gravity? Because remember, it's continually falling around the surface of the object that it is orbiting. Can we derive and utilize the orbital velocity equation for circular orbits? So, how do we derive that? We set the centripetal force equal to the gravitational force from Newton's equation for the universal law of gravitation. We put them equivalently and we solve for v. And can we derive and utilize the equation relating the period of a satellite's orbit and r, the distance it is from the center of the object it's orbiting? And how did we do that? We set the orbital velocity equation and the tangential velocity equation together, and then went to solve for getting them on both sides. Now, why do we want to be able to derive them? That's mainly because these equations are ones we don't necessarily see all that frequently. So knowing, okay, if I just set these two equal, I can figure it out myself, rather than having to memorize them, is a really good, useful tool.